Next, we will move on to geometric sequences. So we have arithmetic sequences and arithmetic series. Now we have geometric sequences. Now, so just like we talked about arithmetic sequences, we're going to talk about these geometric sequences in the same way, describing the pattern that's going from 5 to 25 to 125 to 625. To get to the next number, every single one of these is multiplying by 5. So logically, our next one is 3,125. We're multiplying by 5. In our next one, 2, -4, 8, -16. We're also multiplying by something. In this case, we're multiplying by -2. It might look very similar to one of the ones that we had done in our first section with the exact same numbers, but yeah, we're multiplying by -2. We're going from 3 to 1 to 1/3 to 1/9. There's two ways of understanding it. Either we can say we are dividing by 3 every single time, or we are multiplying by 1/3. So either it's dividing by 3 or we're multiplying by 1/3, which are the exact same thing. Dividing by 3 is multiplying by the reciprocal. These are what are known as geometric sequences. A geometric sequence is where the ratio between consecutive terms comes. So arithmetic is where we actually have a difference, but for geometric we have a ratio. So the ratio, which means dividing, taking term 2 and dividing by term 1. And our formula, very similar to other things, we just have one new bit of information. Tn is still our general term, whichever term it is. Term 1 is still our first term. R is the ratio, which is the new little bit. And n is the term number. So here's our formula. One thing I do need to note is this entire n minus 1 is the exponent. We'll see in section 4 why I'm saying that now, but we're going to talk about that. Alrighty. So first example. Bacteria in a bowl keep doubling by dividing every 6 hours. The bowl starts with 3 bacteria. Find the general term. Now, when I talk about bowl, I talk about kind of a petri dish. So you have your dish where you have anything like that. Of course, it doesn't mean just that. It could also be your counter. It can be your food. Of course, food usually doubles a little bit faster. Bacteria on food will double a little bit faster rate because it has actual fuel to actually do that. But that's besides the point. It's doubling every 6 hours. So if the bowl starts with 3 bacteria, find the general term. So the general term is just what is Tn? Just like term 1, or section 1, where we don't know what n is. So, but we do know what T1 is. It's 3. We also do know what R is. R is the fact that it's doubling. Our R value is 2. And all that is to the power of n minus 1. So how many bacteria are there after 72 hours? So if it's doubling every 6 hours, let's see, 72 divided by 6 is 12. The next part is to plug our bit in. Now, there's one little bit to this 12 that we have to be careful, because at time 0, it has 3 bacteria. At time 6, at 6 hours, it would have 6 bacteria. At time 12, it would be 12. At 18, it would be at 24. So every single time. So the first chance for doubling, it has doubled. So after another 6 hours, that's the second doubling, and then the third. So we have to apply a little bit of logic when we plug our stuff into our calculator. We're going to find out a term, but we want to find out something more specific. We're still going to use some information. We just need to find out what is n. In this case, our first doubling here. So at time 0, this would be our first doubling. But if we plug 1 into here, 1 subtract 1 is 0, 2 to the power of 0 is 1, that'd still be 3. So technically, this is our first term. This, that's our first term. It has 3 bacteria. This would be our second term. This would be the third. This would be the fourth. So on and so forth. What we are actually going to be doing is we are finding out what is term 13. So even though there are 12 time spans of 6 hours, we are actually finding out what is the 13th number in this sequence. 13 subtract 1. So 3 times 2 to the power of 13 subtract 1 is 12. So that's where that 12 actually comes in. As we take that 13 subtract 1, we get that 12, and it all works out nicely then. When we're just plugging our calculator, we have to apply a little bit of logic to it. Now, 2 to the power of 12 is 4,096 times by the 3. So after the span of 3 days, there'd be 12,228 bacteria. You're making copies on a photocopier that are reduced by 40% each copy. What is the length of a 42 centimeter long photograph after 8 copies? So it's being reduced by 40%. Now, this is something that we'll be talking about in pre-calc 30 as what's known as an exponential function. This is all exponential. It's just going to help us deal with our exponential base. Actually, I'm just going to keep this in purple. So something would be 42 centimeters, and now it's going to be reduced by 40%. So one way we can do it is find out what is 40% of this. So 40% of it, 4, is 16.8. So we take 42 and subtract 16.8. So it would be 42 centimeters long first, and then it'd be 25.2. If we continue on with that pattern, 25.2 times by 40%, that is 10.08. So we take our 25.2 and subtract 10.08. 5.2 subtract 10.08. We get 15.12. So the next length of it will be 15.12. Now I'm just doing kind of a point here just to make sure that everything really rolls nicely. In order to find out what our ratio is, so remember, our ratio is used by taking term 2 divided by term 1. So in this case, 25.2 divided by 42. All I'm saying is it's not 40. It's not 40%. 25.2 divided by 42 is 0.6. We can get the exact same ratio by taking, by chance, term 3 and dividing by term 2. So 15.12 divided by 25.2. If you type that into your calculator, you also get 0.6. This is actually our R. So what that's helping us to do is our ratio, our R value. In other words, it's not R value because that's talking about insulation and all of that kind of it, but the R variable in these geometric sequences is what's left. It's also known as our exponential base, but again, that's something that we'll talk about in pre-calc 30 next year, but it's what's left. If it's being reduced by 40%, that would mean that 60% would be left. So you plug it into our formula. Again, I'm just going to leave that n by itself for a second. T1, so go back to the formula. Tn equals T1 multiplied by R to the power of n subtract 1. T1, it's 42 centimeters long first, multiplied by our ratio, which is 0.6 to the power of n minus 1. I'm just going to put the minus 1. In this case, we're also not using 8 because it's after 8 copies. So if it's been copied 8 times, so make 4 copies, original length is 42 centimeters. After 8 copies, it means that we're actually looking for the 9th term. So what is term 9? So again, a little bit of logic that is needed. 0.6 to the power of 8. That's where we get that 8. So if we take 42 and multiply by 0.6 to the power of 8, we get 0.71 centimeters. And just taking a little bit of thought process into our work. Let's go to something a little bit easier, at the same time a little bit harder. Again, we're going to use some stuff where we're going to have to do some manipulation. Tn equals T1 multiplied by R to the power of n minus 1. So in a geometric sequence, the second term is 28 and the fifth term is 1,792. Determine the values of T1 and R and list the first 3 terms in the sequence. So we know that the second term, that term 2, is 28. We don't know what term 1 is. We also don't know what the R is. But we do know that term 2, the second term, 2 subtract 1 is that. Similarly, 1,792 is term 1 multiplied by a ratio to the power of 5 minus 1. So both of these can be simplified a little bit further. T1 multiplied by just R, because 2 subtract 1 is 1. 1792 would be T1 multiplied by R to the power of 4. The last bit of work is we're going to have to do a little bit of manipulation here to try and get these things together. Now, it doesn't really matter which one you use. These are somewhat smaller numbers. Again, it doesn't really matter which one we isolate. T1 times R. Sure, let's divide both sides by R. So that T1 is 28 divided by R. So now we're going to take that and plug it into there. 1792 will be 28 over R times by r to the power 4. What this will allow us to do is reduce some of works. R and 4 would reduce to just be left with 3. So 1,792 would be 28 r cubed. To get the r by itself, we divide by 28. So 1792 divided by 28 is 64. And then we have to find out the cube root of this in order to get rid of that cubed. So finding the cube root of 64. In order to access that, we'd have to press the second, well, actually, we'd have to press 3, press second, then use our power button. Again, this is using the TI-30X2S, and then we just have to type in the 64. By doing that, R is going to be 4. Double check. I'm just kind of doing that in my head, but yes, it is 4. Then we can take that number and plug it all over here to find out what our T1 is. Because T1 is 28 divided by R, 28 divided by 4. Term 1 is therefore 7. So our ratio is 4. What we're doing to get to our next number, 7 times 4, is 28. So yeah, that works. Term 1 is 7. Our ratio is 4. So for the first 3 terms, our first term would be 7. Multiply by 4 to give us our second term, which is 28, which is good. That was stated. 28 by 4 to get to our third term, to be 112. Alrighty. Let's have a little bit of applied math here. A modern piano has 88 keys. Kind of a little Jeopardy question for you. So 88 keys on a modern piano. The frequency of the notes range from AO, kind of the original A, the lowest note at 27.5 hertz. If you're dealing with your sound bit with physical science, hertz frequency, to C8, the highest note of the piano, which is 4,186.009 hertz. Now, obviously, this is rounded. Both of them are rounded, but just what works out the best. These frequencies are geometric. What we're going to do is determine the ratio from the lowest note, AO, to the fourth note, C4, at 32.7 hertz. In order to do this, it's going to be really nice to identify what our different terms are. For example, we already know that term 1 has a hertz of 27.5. We also know some N, and we know, no, I'm just going to say, we know term 4 is 32.7. So overall, in order to use our formula, Tn equals T1 multiplied by R to the power of n minus 1. The only thing we really don't know is what is R, what is our ratio? And that's exactly what the question is, determine the ratio. The beautiful thing is, if we are looking at Tn, our fourth term has a frequency of 32.7. Term 1 is 27.5. Trying to find out our ratio, well, 32.7 is term 4. So we can use 4 minus 1 in here. So just saving a little bit of work here, we can divide both sides by the 27.5. So 32.7 divided by 27.5 is 1.189. I'm going to leave that in my calculator. That would just give me the R to the power of 3 And then I'd just be finding the cube root of this. So cube root. The reason I'm leaving that on my calculator is because I can actually formulaically solve this stuff. Our ratio is the cube root of 1.189. So I'm going to type in 3 second my xth root of my previous answer, and I get to 1.0594. Now I'm also going to still keep on leaving that on my calculator. 1.0594, 28584. We're going to verify that this is actually the ratio from A by using AO and C8. So since C8 has a frequency of this, .009, we're going to confirm that term 1, which has a frequency of 27.5, our ratio of 1.0594, blah, 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 to the power of, well, how many times are we looking for? Should be, since C8 would be the 88th key, this is would be the one case where we're actually looking for 88 minus 1. I'm just going to quickly double check that, make sure I'm telling you the right thing. Yep, that is right. So if we take 27.5 and multiply by 1.0594 to the power of 87, because that's 88 minus 1. So I have that 1.0594, so on and so forth in my calculator cell, power 87, multiplied by the 27.5. I get 41.74.16. Well, that's not exactly right because it's not 4186.009. That is simply because this is a rounded value. So is this. So these two really are close enough. They are only, what, 12 away from each other? 12 hertz away, which is not a huge difference. So we're good. All right. That allows you to go have some fun.